So in this section 3.7, which is free my mechanical vibrations, all we're doing is taking 3.1 to 3.4 and we're changing the letters A, B, and C to actually mean something. Mass, damping, spring constant. So that's all we're doing. We're just making 3.1 to 3.4 word problems, if you really want to think about it that way. So let us look at the differential equation of the form ay double prime plus by prime plus cy equals g of t, given y of 0 equals y naught, and y prime of 0 equals y1 in terms of a mass spring system. So I'm going to derive the equations of motion here through Newton's second law. So the next 10 minutes, if you're watching this video, it's just derivations of this equation. If you don't really care and you just want to know like what's the equations, what do I need to know for the exam, you could just skip ahead until you get to the final part of this derivation and your equations are all there. So, but there is value in kind of seeing how this whole thing interacts. So I would say it's kind of worth it. So free undamped motion. So there are some words you want to pay attention to. So like the word free, what that means is G of T is 0. There is no acting force on your system. Undamped just means that there's no friction, right? The spring system can kind of behave however it wants without any friction in its system. So imagine you have a spring just hanging out. We draw vertically just to make it look nicer. Um, and this spring has a length L. So we'll call this L. And when you attach a mass to it, it's going to stretch, right? So we draw that same spring like that. And again, this length right here is still L. But as soon as I attach a mass to it, it's going to stretch further down and be right here. So we have a mass m. And that distance we stretched it down, we'll just call it something like s. So s. And so let's just define what those mean. So L is equal to the natural length of the spring. And then s is going to be the distance to equilibrium. So that is the moment where the spring is basically not able to pull it back, but it's also not being pulled down, essentially. And if I were to do something like pull this mass down even further, right? So let's say we have this right here, and then we just pull it down further like that. Well, we still have our natural spring length, that's L. We still have the distance to equilibrium, wherever that was, right here. But now we have this even further distance away, wherever the spring is, and we're going to call that x. So the distance from equilibrium. So that's what x is equal to, distance from equilibrium. Like that. Now, here's something that you learn in physics. There's this notion of something called a free body diagram, which basically says you can analyze a system by just ignoring things, essentially. I mean, you can pick something, like let's say the mass, and then I can devise forces and define coordinate systems however I want. I can draw them in the directions that I want. I am basically at liberty to kind of define whatever I want. Whether it's correct or not is to be debated, but I'm allowed to do that. So, one of the things that we're going to define is what is the equilibrium, moment or distance. And so for us, it's basically this. Another thing that we define as well is at what point are the forces coming in or out of, in the sense of like, is it at the inside of the mass? Is at the edge of the mass? Something like that. And typically, most people will draw it wherever the center of mass is, which is typically the center. So that's why I draw the line in the middle of the mass versus like the bottom or the top. Most people like to use the center of mass. Again, this stuff is not that important for the derivation, but just things that if you're working on dynamical systems and stuff like that, it is things that you do think about. I have had problems where defining like we call like a reference point, your starting point, at the center of the mass versus like the bottom or the top of the mass just makes the math a little bit easier or more difficult. So what this I am saying here now is essentially this is kind of like my 0 point. And if I go up, I am going in the negative direction. And if I go down, I am going in the positive direction. Now, that might seem counterintuitive, but what I'm really saying is for the sake of our algebra and how we're going to derive everything, it makes more sense for me to discuss going downwards as a positive motion and going upwards as a negative motion. And the reason for that is because most of the time you're pulling the mass down, which is the more common motion, which means that makes more sense to be positive. Usually the motion that's more common tends to be positive versus negative. So going down is positive, going up is negative, right? That's just kind of what I'm saying here. And we're going to use all of this information to now create some equations using Newton's second law. But that kind of sets up the groundwork for what we want to do. So moving on, we say, okay, we're going to make a free body diagram. And we're going to look at the mass. Okay, so here's M. Again, if you wanted to, you could just draw a point because we're going to centralize it to the center of mass. And there are two things acting on this mass, right? There is gravity, which is pulling it down. So gravity, the force of gravity. And then there's something pulling it up. And that's going to be the spring. So the force of the spring. And Newton's second law says that the sum of the forces equals, mass times acceleration, right? So let's write that down. Newton's law, second law, states that the sum of the forces equals mass times acceleration. Not only that, Hooke's law. So Hooke's law is about how springs behave. Hooke's law states the force of a spring is proportional to its displacement. Now, this only works for small displacement. If you stretch a spring too much, it's going to bend and not work anymore. But basically, I'm saying that however much I pull the spring, the force is proportional to how much I pull it by. So to define our variables, the force of the spring is Fs. And then the force of gravity is Fg. Now, gravity is pretty much the same thing always. 9.8 if you're talking about U metric, 32 feet per second squared if you're talking about US customary. So what we want to describe here is how the forces are behaving with the position and essentially the acceleration first, and then we want to get to position. So we're going to say, okay, let x be equal to the position of mass, x prime be equal to the velocity of mass, and x double prime be equal to the acceleration. Now, some textbooks, especially in physics textbooks, they will say x double prime is equal to x double dot. So you might see like a dot notation. That just means your time derivative, really. But I'm going to use the prime notation here. Okay. Using Newton's second law, the sum of the forces equals mass times acceleration. And I'm just going to swap the mass acceleration to the left side. So the mass acceleration is equal to the force of the spring plus the force of gravity. Oops, I'm going to do it the other way. Doesn't matter, but this just makes it look nicer. Okay, so force of gravity and the force of the spring. Now, what determines gravity? Well, gravity is an acceleration, right? G is equal to gravity, acceleration, which means it's going to be defined by mass times acceleration. Mass times acceleration, mg. Okay? So the force of gravity is mg. Now, what defines the spring constant? Well, sorry, wrong one. Mass times gravity. Well, we said that Hooke's law states that the force of a spring is proportional to its displacement. So we're going to say the force of the spring is equal to K, which is the spring constant. That's the proportionality equals K. And then its displacement X, or, distance or position, really. Um, so we're going to say plus Kx. Now, here's the thing. We have to pay attention to what directions the forces are going relative to the defined up and down, what's positive and what's negative. So earlier I said going up is negative and going down is positive. So that's positive. That's negative, which means Kx is negative, according to our free body diagram definition. Now, if you're wondering, what if I did it the other way? What if up was positive and down was negative? You get the same answer. It would just, the signs would be backwards. Here's the cool thing about free body diagrams. If you draw an arrow in one direction and your answer is negative, all that tells you is that on your free body diagram, the arrow was going in the wrong way. It should have been going the other opposite way. This is very common in like civil engineering, where you might assume a force is like in what we say compression, but then your answer is negative, which tells you that the actual force was not in compression, but it was actually in tension. The answer is not wrong. It's just your interpretation of it initially was not correct. It was backwards, but the answer and values are still the same. That's why a lot of the times you take absolute values with these numbers because we don't care about directions a lot of the time. We just care about what the magnitude, we would say, or the actual force value is because that's what's important, not the direction itself. So this is our main equation here, and we're going to manipulate this so that way we can get the equations of motion. So this is where we're going to have our starting point. Now, beyond this equation, so we're going to go on to the next side, we're going to say, okay, let A, the acceleration, be equal to x double prime, right? Acceleration, we defined earlier that x, the second derivative of x, is the acceleration of mass. So then mx double prime is equal to mg minus kx. And there is our equation, right? Like this is the actual equation of motion, but we want to be able to kind of make some nice assumptions, and we're going to use this idea of equilibrium to kind of find a relationship that we'll use later. So, if the system is at equilibrium, so this would be the second picture earlier. So, the middle one. So, put 1, 2, and 3, the second picture. Then when you're at equilibrium, there is no acceleration. Now, that doesn't mean you're not moving. You can be moving and still be at equilibrium. The easiest example is a train. If a train's going 70 miles per hour the entire time, you don't feel it. You feel like you're stationary, like you're not moving at all. That's because what you feel is acceleration. So when you feel movement and speed of like a car or a train, it's because it's accelerating. When it's not accelerating, there is no feeling of it moving. You feel stationary, right? So if there was no wind and you jumped up on a train, you would fall right back where you were standing because that's just kind of how it works. But if you jumped up and you flew off a train, it's because the wind resistance knocked you off, not because of any other, gravity or anything like that. It's not like gravity lost you. It's the wind friction that got you. So if the system is at equilibrium, then the sum of the forces is going to be equal to zero because mass times acceleration is zero because x double dot is, sorry. Yep, and so forth equals zero, meaning, yeah, x double dot is equal to zero, and we get zero equals mg minus kx. So this is our equilibrium relationship, which means, if you think about it, the force of gravity and the force of friction are canceling each other out. That's really what we're saying, right? If you think about it, mg is equal to kx. There's a balance. They are in equilibrium. So that's nice. We have this nice relationship. So we're going to use this in the next step, which is how we're going to get the full equation of motion that we can work with. So when motion is applied, then the system is not in equilibrium. And if we draw our free body diagram, so the force of the spring and the force of gravity, right? It's still the same forces, but the force equations change. Well, gravity never changes. Gravity is always going to be mg. That's just how gravity works. It's constant, which is nice. However, the spring is going to change, right? Remember, spring is proportional to how much it's moved. So it's still equal to k, but according to diagram 3, in the first one, I only moved nothing, right? I was in equilibrium. My movement is zero. But in the second case, I have moved a distance of x plus s, right? I have gone this entire distance, so that's what we're going to say. So it's going to be equal to, well, actually, I take it back. For the equilibrium, you moved a distance of s, right? So that's where the s comes into play. You've actually did stretch. But in the case of the uh, non-equilibrium, it's k. Sorry, s plus k. So make sure to do this in the correct order. X plus s. And just, I guess going back, we could actually, we could use S right there, or do I, yeah, we should use S. So just to make this more, that should be S, and that looks good. Yeah, that's S. That's X, and then at equilibrium. Oh, I see what I'm saying. No, this is X. This is perfectly fine. It's the next slide. Okay. Here we go. That's where I should have changed it to S. S and S. There we go. At equilibrium. Apologies. Everything else before then was good. So we're going to now go beyond equilibrium, which is where the x comes into play. So then our equations of motion. So using Newton's second law, actually, let's just second law. the sum of the forces equals mass times acceleration. And so we're going to say mass times acceleration is equal to the force of gravity plus the force of the spring, which is equal to mg plus, or I guess to say minus because it's going in the opposite direction. We're going to say x plus s, like that. And if we distribute the k value into it, mg minus ks plus kx, like that, and there's a reason I did it in that order, is because we know from right above, right here, that mg minus ks is equal to 0. So this whole thing right here is 0. So what we end up getting is mass times acceleration is equal to kx. But not kx, sorry, negative kx. I forgot to distribute my minus sign right there and right there. So ma equals minus kx. Well, that kind of looks like what we had earlier, but now it's no longer at equilibrium. It's at any point beyond equilibrium, right? So letting a be equal to x double prime, we get mx double prime equals negative kx. And you might think, okay, well, we want this to be a nice equation so we can move everything over to one side. And moving everything to left side, we get mx double dot plus kx is equal to 0. And that is the equation of motion. Now, this is a very specific type of equation of motion. This is what we call the free, undamped equation of motion, or simple harmonic motion, I think is another name for it. So free simple just means it's equal to 0. It's homogeneous. There's no force acting upon it. Undamped means there's no friction. I also think harmonic means no friction because it's going to be just sine curves that are going up and down, up and down. So that's our equation. Like that's what we're solving. And if you really think about it, if you were actually to go back to 3.3 and look at a problem that we did together, hopefully I can find it very easily right here. We are really just solving this problem right here. We already know how to do this problem. It's this one. This is the problem that we're solving for, where there is no coefficient of y prime, right? There's no y prime, which means we're going to have purely imaginary answers. So that exponential function is not going to be in play. That exponential function, that's your damper. That's what actually causes it to lose energy. Here, there is none. So that is the main equation. So now we're going to solve this equation so that we can get a solution. So assuming m cannot be equal to 0. Okay, if m is 0, that means you have 0 mass, which doesn't make sense because if you have 0 mass, then it can't move the spring. So it's a very logical assumption to say that m does not equal 0, right? Um, and k does not equal 0. Otherwise, the spring doesn't do anything. So these are very natural assumptions to make because otherwise the problem basically reduces down to something trivially uninteresting. Okay? So assuming m does not equal 0 and k does not equal to 0, then we can solve for x of t, the equation of motion. So the answer that you are looking for here, if you're wondering like, okay, I'm solving all this, like, what does my final answer tell me? It tells you how the mass moves. Because we can always kind of know how things are accelerating because of gravity, but the at the end result, what we really want to know about a system is like what it's doing. What is its movement? Like that's what we want to know. So like that's what we're solving for is the equation of motion or the displacement or how it's, what is its location, right? That's what we want to know. Okay. So if we're going to solve this, so isolating, actually, no, let's not do that. Using quadratic formula, uh, x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So then x is equal to 0 plus or minus the square root of 0 minus 4m times k all over 2 times m. And then this is going to be equal to the square root of negative 4mk all over 2m. And so what we end up getting is 2i square root of mk over 2m, which is equal to I square root of mk over m. Like, that's the solution. Now, that's not a very nice solution if you ask me, right? So we can actually simplify this. So there's a property that we can use here, which is going to be this. I. We can break up radicals by, if they're positive, which they are. And then this is equal to I square root k over square root m, which is then equal to I square root m, sorry, k over m. And there you go. So this right here is going to be your beta value for when we're solving for sine and cosine, right? So using our known solution for complex roots, y is equal to e to the alpha t cosine of beta t. Oops, I forgot the C1. Plus C2 sine of beta t. Then y, sorry. And we're going to use x now, sorry, because it's x. So this is a one case where it's x instead of y because we're using x as our displacement. So since our root was, and let me go back here. I'm going to change this to r because our root is r. We like to call it r, right? So since our root was r equals I square root of k over m, this means that alpha is 0 and beta is equal to square root of k over m. And our equation of motion is c1 cosine square root of k over m plus c2 sine square root of k over m. And that's it. We have solved the equation of motion. Don't forget t there. And that's how we model how the spring is moving up and down, or however the motion is being described. Now, what this means fundamentally is when you're doing a problem, number one, you don't have to do these derivations. These derivations are nice, very helpful to understand. You can skip straight into the mx double dot plus kx. Like you know what the equation is. Identify mass, identify the spring constant. You don't even have to solve the auxiliary equation. Like you don't have to do the quadratic equation. If you memorize what the final answer is, you just need to know what K and M are, which you're going to have to know what the mass is because without knowing the mass, there is no problem. The spring constant, I can give you enough information to solve for it, or I can just give it to you directly. So in theory, you can always just skip to this very last step if you know enough information, or if you can easily find the information, which you can most of the time. So, this is one of those things where you don't want to do more work than you need to. So if you have all of the information, you can just skip to this final step. You don't have to solve for the entire equation. It's already been done. Now, because we're going to be dealing with frequencies and stuff like that, there is another interpretation of this equation that is the same thing. Like it's the same answer. It just looks different. So we're going to talk about that now. So, um, for convenience and notation, we can say, or sorry, we can define this variable omega, which is going to look like a W, but it's omega. So we're going to say we can define omega squared as k over m. What does that do for us? It just makes the algebra easier. Okay. Then x, sorry, let's do it over here. X double dot plus, sorry, mx double dot plus kx equals 0. Well, if I divide mass over to both sides, k over m equal to 0, like that, then I recognize, oh, I have k over m. I can substitute it with omega squared equal to 0. I forget the x. And if I use the quadratic equation, right? So I'm going to do the quadratic equation on this one now. We say, okay, r is equal to 0 plus or minus the square root of 0 minus 4 times 1 times omega squared all over 2 times 1. And we get the square root of negative 4 omega squared over 2, which is equal to negative 2i. Sorry, there's no negative here. Sorry, 2i omega squared, no, 2i omega, because the square's gone, over 2, which is equal to I omega. And that's our root. Oh, I can't forget the plus or minus. I did that. Did I write that on the last one? No, I did not. There was a plus or minus here the entire time. Not that it mattered. We know that they come in pairs, right? Well, it does matter. I take it back. It does matter, but we know that complex roots always come in conjugate pairs. So I did forget the plus or minus on all of these. Hopefully someone doesn't, email me saying like, "Hey, you made a mistake." Because I have this happen sometimes that people will watch it, they'll see a mistake, and then they won't finish watching it, and then I fix it later. So plus or minus. Yep, we're good to go. All right. So plus or minus, plus or minus, plus or minus, right? So this again here is beta. So x of t is equal to c1 cosine omega t plus c2 sine omega t. So just looks nicer. Is it any different than this equation up here? Absolutely not. But sometimes instead of giving you k or m, they might tell you, hey, the frequency of the problem is omega equals 5, and then you can just use this equation as omega, right? So it just comes down to what kind of context are you given for the problem. So these are interchangeable. They both mean the same thing. So whichever one you prefer, stick with it. So the graph of x of t will most of the time look like this. It'll either start at the top or the bottom, and it just is a sine curve going up and down and up and down. Now, because it has no friction, no damping, it's never going to go to 0. And because it's free, there's nothing extra acting upon it, so it's never going to go like to infinity or something like that. So that's a good thing. And that right there basically summarizes the derivation of this entire equation of motion. So if you're wondering, okay, out of all of that, what do I need to remember or understand? It's basically this, okay? So in summary, a y double prime plus b y prime plus c y equals 0 is now become mx double prime plus uh, kx equals 0. And then y equals c1, sorry, y equals e to the alpha t c1 cosine beta t plus c2 sine beta t has become x of t equal to c1 cosine omega t plus c2 sine omega t. That's it. A has become M, C has become K, and then our equation has become C1 cosine omega t and C2 sine omega t. In summary, for free undamped motion, and in the future, we'll just generalize this where we do allow for damping, we do allow for motion, force motion, and we're just basically adding more characteristics. So right now we've removed the y prime. Now the next thing we're gonna do is we're gonna add y prime, and then after that we're gonna make 0 not 0, and then that's 3.8. So making 0 not 0 is 3.8. Making b not 0 anymore is where we talk about damped motion. So before we do an example, let's just talk a quick moment about units. So we're going to be using US customary, and we're going to be dealing with metric or SI for standard international. Okay? So you have to understand that there are two things that are different that you kind of use interchangeably that is technically not correct, and that's the difference between mass and weight. But let's talk about length first. That's the easy one. So length is going to be, feet. Sorry, we'll start with the smaller one. Um, Inches, feet. Okay. And then miles, technically too, but we're not going to go that far in these types of problems. So inches and feet. Remember, 1 foot, 1 foot equals 12 inches. Like that. That's all you got to know. And I guess, oh yeah, you could do the yard. 1 yard is equal to 3 feet, right? Inches are the smallest unit of length we have in US customary. For metric, for length, we're going to use the meter, right? And for meter, it's all going to be about what the prefix is, right? Centimeters, millimeters, and all that. So, and then remember, these are units of 10. Sorry, magnitudes of 10. So 1 meter is equal to 100 centimeters. It's equal to 1,000 millimeters, right? For the most part, with these types of problems, you're going to be either talking about meters or centimeters. We're not going to go too small into the millimeter range and stuff like that. But uh, generally speaking, you want to have consistent units is what we're kind of aiming for, right? And we will not make you convert between metric and US customary just because there's no exact conversion, which means it creates a rounding error. So, um, but it's always a good idea as an engineer to memorize one conversion, or we call them bridges. So for me personally, I've always memorized that 1 inch is about 2.53 centimeters, and that's the only one I remember. That's how I always bridge them together, right? And then 1 kilogram is 2.2 pounds or something like that. So I always know at least one, right? And then the other one that is going to be important is mass. And then by extension, weight. Okay. So first, let's start with the metric because most people know what metric mass is, and that's the kilogram. Sorry, the gram, right? So it's the gram. So 1 gram is equal to, well, we're not going to usually go, we don't usually go smaller than a gram. We're going to say 1 kilogram is equal to 1,000 grams. In the context of engineering, we usually don't go below grams. Like usually a lot of things we talk about aren't that small. Now, if you're like in chemical or like, in that kind of realm, then yeah, you probably go into smaller realms of like centigrams and milligrams. Okay, we're talking about milligrams. We all use milligrams. What am I saying? So 1 gram is equal to 1,000 milligrams. But usually we try to stay in the gram realm just because the things that we talk about aren't that small. But again, if you're like in chemical or biomedical, then yeah, you probably do go into the smaller realm. So that's mass. For US customary, it's actually a different unit that most people don't know because we actually never use it. It's called the slug. That's it. It's a slug. I don't even really know slugs too much. I could look it up right now. But it's just our measurement of mass. Again, we usually use grams or kilograms. So you will probably never see a problem with slugs, honestly, at least not in this class. Now, weight is the thing that we do use in US customary that people often sometimes confuse with mass. And so the weight is the pound, right? So pounds or ounces, but we're not going to do ounces in this class. And then the weight for SI or metric is going to be the Newton. Okay. So if we're talking about weight, it's a Newton in metric and it's a pound in US customary. So don't think that kilograms are a weight, they are a mass. Okay, that is very important. And something else that you have to realize is force is a weight. So weight is a force, right? So if we're talking about forces, we're always talking about newtons or pounds. If we're talking about mass, it's a, you know, gram or a slug. So this is important because you're going to have to do some conversions where you're converting masses into uh, weight. And the way we do that, okay, so weight is equal to mass times gravity. That's the key equation. Weight is equal to mass times gravity. And gravity is 32 for US customary, and it's 9.8 for SI. So there will be problems where you have to do that. But also, this relationship allows you to convert weight into mass, which is, weight divided by gravity, right? So there's a difference between the two, but they come from the same equation. So now we can finally do a word problem after all this talking. So a mass weighs 2 pounds, stretched 6 inches below equilibrium. At t equals 0, so initial time, the mass is released from a point 8 inches, sorry, 8 inches below equilibrium. Sorry, this below equilibrium is not there. I just copied the wrong line, so below equilibrium. So a mass weighs 2 pounds, stretched 6 inches. So the beginning part is the equilibrium length. I just copied below equilibrium because it was right below it. Below equilibrium with an upward velocity of 4/3 feet per second. Find the equation of motion. So essentially what I'm asking you to do is solve a differential equation, but I don't give you a differential equation. You have to know the differential equation. So you have to identify it. Well, is this a damped versus undamped problem? Does this have free motion or is it forced motion, right? These are things that you have to think about. But here's the thing. If you remember, hey, I already know what the solution to that differential equation is. As long as I can find those specific things, I could skip a lot of the work, right? So here I'm going to do all the work, but I'm going to tell you if you get comfortable enough with this, you could actually skip a lot of it, right? So step one, as we try to in every single problem in this class, is what's a good formula? Well, I'm just going to write down this formula. It's the only one I have so far, right? X double dot plus kx equals 0. Oh, can't forget about m. Now, that means I need a mass and I need a spring constant k, okay? So step two is to find mass. Find m. You can always find that because they have to give it to you in some way. So they tell you a mass weighs 2 pounds, right? So force is equal to, sorry, not force. I mean, it is force. The weight is equal to mass times gravity. So I'm told it's 2 pounds, and I don't know what mass is, but gravity is 32 feet per second squared because that's US customary. And so if I solve for m, I get 2 over 32, which is 1 over 16 slugs. Again, you don't have to worry about carrying slugs around. It's there, right? So that's our mass. And we now know what m is, which means all I need to solve for is k. So step three is find k. I want you to think so far. The only thing that's differential equations about this entire process is the formula. Everything else is kind of algebra, right? Finding an unknown variable, finding a k value. We've done this before in, algebra. So find k. So you have to know Hooke's law, right? It's one of those equations that they expect you to know. And Hooke's law just says F equals kx, right? Um, the force of a spring is equal to its proportional constant k times the distance it stretched. Now, if you're wondering, can k be negative? We always assume it's positive. So if your force is negative, just make it positive, right? We take the absolute value actually. So sometimes you'll see something like this, where they say like, oh, take the absolute value of the force or something like that. So just always use the positive version of all the numbers and you'll get the same answer. So I am told that a mass weighs 2 pounds and is stretched 6 inches, right? However, this is where you got to be careful. You need to decide what units you're going to use, okay? So notice in the problem statement, I have 6 inches and I have 8 inches, but I have feet right here. Right now, we have an inconsistency in units, which means I have to commit to one of them. Once I use one unit, the rest of them have to be the same. So let's go back and let's add that as a step, right? So let's that's fine right there. Let's move step two, move it down a little bit, and call this step three now, and we'll call this step four. And we're going to say step two is check units and convert if needed. Okay. So, me personally, I like to work with the smallest numbers possible. But I do understand some people don't like fractions. So, if you convert inches into fractions, sorry, feet, you have to convert them all into fractions. Whereas if I convert feet into inches, typically they tend to be not fractions. So, it's a personal preference. Me personally, I'm going to convert everything to feet. I just like working with smaller numbers. Okay, so I'm going to do inches to feet, just so I know that that's what I'm going to do for all of my problems. Okay, and you can do it as soon as you want. So my force is going to be k times 1/2 feet. Okay, right? So this right here is 1/2 feet, and this right here is 2/3 feet. And you can do all in inches if you prefer that. It's a personal preference. Whoops, force is going to be 2 pounds. I'll tell you right now, it's better often to do it in feet anyways, because a lot of our units are derived around feet. It's the same thing with meters. We want everything in meters usually, and kilograms, because everything is kind of built on kilograms. Okay. In fact, I think slugs are designed around feet, and kilograms, sorry, not kilograms. What's the other one? Yeah, no, sorry, gravity. Sorry, gravity is around derived around kilograms and pounds. Sorry, and feet, because feet per second squared. So then we divide over the 1/2 and we get 4 right there. So K is equal to 4. Step 5 is to plug in formula. So we have 1/16 x double prime plus 4k, sorry, not 4k, 4x equals 0. And then step 6 is to solve for x. Solve for x of t. So we're only doing free motion undamped, so there's going to be complex. Here's an algebra trick for you if you ever run into this case. We don't like x double prime having a number in front of it, so I'm going to multiply everything by 16. And so what I end up getting is x double dot plus 64x equals 0. And then now I do my whole analysis, right? So r squared plus 64 equals 0. R squared is equal to negative 64. So R is equal to plus or minus 8i, right? That's what it is. And we go from there. So our equation of motion is going to be equal to C1 cosine 8t plus C2 sine 8t. And so now we have the general solution to the equation. Now, you could have also, just to throw this out there, you could also realize m equals 1 over 16 and k is equal to 4. So x of t is equal to c1 cosine square root of 4 over 1 over 16 t plus c2 sine square root of 4 over 1 over 16 and then x of t is equal to c1 cosine ht. So what I'm trying to get at is you don't have to go through the entire process if you recognize that you have all the information. You get the same thing, which is great. You can show as much work as you need to right there. So we have solved the differential equation, and step 7 is solve for C1 and C2 using initial conditions. And so what are the initial conditions? Well, unlike previous problems, these are not going to be super obvious like they're numerical. Usually they'll say them in words. So what words are we looking for? The point is released from a 8 inches below equilibrium. So they say 8 inches below equilibrium, which then means the position at 0 seconds is equal to negative 8 inches. But we don't want inches, we want, so we want to convert inches into feet, negative 2/3 feet. And then we say upwards velocity. That's positive, not negative. What was that, 4/3? And so that means x prime of 0 is equal to negative 4/3. feet per second. Now, if you're wondering, why is below positive? Remember, at the very beginning, I said anything below equilibrium is positive, anything above equilibrium is negative, and going upwards is negative and going downwards is positive. So if this is equilibrium, then this is negative, and then this is positive, and that's zero. So that's why. You just got to understand that that's how we define it. So we have our initial conditions right here. Which means, as always, I have to take derivatives and solve for A and B. All right, that's kind of the natural thing we have to do here. So x of 0 is equal to C1 cosine of 0 plus C2 sine of 0. And that means we get 2/3 equals C1 times 1 plus 0. So C1 equals 2/3. There we go. Remember, sine of 0 is equal to 0, and cosine of 0 is equal to 1. You're going to use it so much in this section, so you got to know. So then x prime of t, so finding derivative of x of t. Got to use the chain rule here, very important. Uh, -8 c1, so derivative of the cosine is the negative sine, right? And then the derivative of the sine is the cosine. You know what? Just because I think it'll make more sense if I do it this way for some people. C1 cosine of 8t times -8. The sine is the cosine. Like that. I just want to make sure people can see the derivative being taken like that. And then the derivative of the sine is the cosine. Like that. So chain rule in effect. Oh, that should be sine. There we go. And then using x of 0 prime equal to 4/3 negative. -4/3 is equal to C1, sorry, -8C1 sine of 0 plus 8C2 cosine of 0. So -4/3 is equal to 0 plus 8C2. And so we're going to divide both sides by 8. And so C2 is equal to -1/6. Thus, our equation of motion is equal to 2/3 cosine 8t, 8 times t, not 80, minus 1/6 times sine of 8 times t. And there it is. That's our equation of motion. And going back in this problem, just to make sure we're clear on something, if you were to draw this system, right, basically this is what's happening. So that's our mass, and this is equilibrium. Call E for equilibrium. So the problem starts where the mass has been shifted down here. So this is t equals 0. And we have a distance of 8 inches, right? And then I release it upwards, right? Because when I let go, it's going to naturally go upwards. I basically almost think of it as like you're kind of pushing it up with the force, but that's the only force that ever touches it. So it's an initial movement, and then there's nothing else touching it afterwards. That's basically what I'm saying. And this is the 4/3 feet per second. So that's essentially what's going on in this picture. If you're above equilibrium, then your initial condition will be a negative position because anything above equilibrium, it has to push it down, by uncompressing or, stretching out. And so we call that negative. So that's essentially what's happening in this system in terms of its movement. Now, let's look at what this graph would actually look like. So if we actually were to plot this, it would look something like this. And I want you to notice that we don't care about anything before zero because, there's no such thing as negative time in our context here. So if you notice that our initial condition was, from what I recall, 2/3, right? Or 1/2. Nope, it's really from a point of 2/3 below equilibrium. So notice that 0.6667 is 2/3. That means that's where it starts. It's below equilibrium. It's in a positive state. And then when I release it, it's going to go down. And then after 1.6 seconds, it reaches back to equilibrium. And then if you keep going at 0.362 seconds, it is now at negative 0.68, which means this is the point where it has basically compressed as much as it can, and then it shoots back out. And then over the course, it'll shoot back up to 0.68 and then negative 0.68, right? So, like, that's the maximum and minimum uh, distance it'll displace forever, right? And because there's no friction, it never, deviates from this because it just goes back and forth, right? If you just imagine a spring bouncing back and forth, nothing there to stop it. And because this is a sine cosine curve, it does it in a periodic fashion, right? It'll always take the same amount of time to go back and forth, no matter how long you're doing this for, right? So that's kind of what we're visualizing here. So if I were to change the initial position, it could change the curve in the sense of that it just starts somewhere else, right? But fundamentally, it should resonate back to here, essentially. So that's just kind of what we're looking at in the context of what the picture looks like when we actually solve for this. We're seeing how the behavior of the system is behaving. And in the long run, if I want to ask you, like, how does the system behave forever? Well, you could just say, oh, it just bounces back and forth between negative 0.68 and 0.68 feet, right? So that's kind of what we're looking at in terms of the final solution. So through this section and the next section, you're going to come across some vocabulary words. So let's just mention them now. Vocabulary. Um, so the period of motion is the time for one complete cycle is defined as uh, t equal to 2 pi over omega. Right, so that's how we're going to define it. So the period of motion is t equals 2 pi over omega. And if you've taken physics or what any other class like that, you've definitely have seen these equations, maybe different letters, but I think sometimes they might use like, F or something like that. So, but we do have one with F. The extreme displacement is going to be essentially kind of like the amplitude, is A equal to the square root of C1 squared plus C2 squared. The circular frequency is omega equal to the square root of k over m. And then the natural frequency is going to be f equal to omega over 2 pi. So again, just some vocabulary and words and equations that you will see when doing some of these problems. So now we're going to discuss free damped motion, which is basically saying, okay, now we're going to say that there is this idea of friction, right? What happens when we have to deal with friction? And is there anything different? And the reality is, not really. It's kind of the same thing. It's going to be that all you have to do is an extra, it's like basically going back to 3.1 and 3.4. Now you can do complex real and repeated roots, right? So that's kind of the only difference. Some examples of systems that have to deal with damping. Imagine you have a mass, but this mass now is underneath water, right? Well, as it's moving underneath the water, there's friction in play, right? Or maybe more commonly thought of, imagine you have a cylinder which represents a piston, and you are using some kind of, liquid, which is usually air and gas, and you're causing it to explode and it pushes it up and down, right? There's friction of how much force we want to be allowed. And so that's kind of what we're analyzing, right? So you can do many different types of systems, but fundamentally, the mass is going to have a new force, right? So if we do our free body diagram, we have the force of gravity, we have the force of the spring, and now we have the force of friction, I will say, right? So we still use Newton's second law, right? So using Newton's second law, the sum of the forces equals mass times acceleration, which means mass times acceleration is force of gravity plus the force of the spring plus the force of friction, like that. And if we replace everything, so using A equals x double prime, then mass times x double prime is equal to force of gravity plus force of spring plus force of friction. And then knowing the relationships that we have built up until this point, mass times acceleration. So we know this is equal to negative kx, right? If we go back to what we talked about earlier, this was negative kx, okay? And not in equilibrium. And then the force of friction is going to be new. Okay. So this is not something that I'm going to derive in this class. This is just something you would learn. But we would learn that the force of friction is proportional to the velocity. We will define it as the following. Force of friction equals, I personally use beta, but I'm already using beta for complex roots, so I'm gonna use a different letter. And the letter that they use in the homework from what I'm seeing is C, which I don't like because we already use C for something else, but I'm just gonna use C here. So Cx prime, right? Because again, it's velocity and x prime is velocity. So mx double dot is equal to negative kx. Now, because it's going upwards, right? It's going up. It's going to be minus cx prime, like that. So notice that we have that. Also note that c will always be positive. We always define it as a constant of proportionality that's constant, or sorry, positive. So it's greater than zero. So that's our equation. And if we move everything over, that is our governing equation right there. Which, if you really think about it, it's just AX, right? It's just ABC, Y double prime, Y prime, and Y. But now it is just different letters. It's the same equation, different letters. So nothing new, really nothing new. Now, if we want to solve this differential equation, so solving the differential equation, we will make some manipulations manipulate some variables out of convenience. So I am telling you right now, I recommend if you have time and the desire to do so, to solve the differential equation using the letters that you see right now, you'll get the same answer. It'll just be very ugly. So what someone realized is that I can make the answer look a lot nicer if I make these two changes to the equation, okay? Where they come from is straight from the fact that if you do the ugly manipulation, you realize, okay, if I actually made this into this and this into this, everything would simplify very nicely and my life would be easier. So I'm telling you right now, this is just something out of convenience. So the first transformation we're going to make is that we're going to say C over M is equal to 2 lambda. Where does the 2 come from? If you remember, we have to divide everything by 2 from the quadratic formula, so that 2 is just there to make life easier. And the other one is k over m is equal to omega squared, right? So mx double dot plus cx prime plus kx equal to 0 becomes x double dot plus c over m x dot plus k over m x equals 0, which then means x double dot becomes 2 lambda x prime plus omega squared x equals 0. Again, why are we doing this? It's just because the quadratic equation looks nicer. So using quadratic formula, our root is going to be equal to negative 2 lambda plus or minus the square root of 2 lambda squared minus 4 times 1 times omega squared all over 2 times 1. And we get negative 2 lambda plus or minus the square root of 4 lambda squared minus 4 omega squared, right? And notice that another reason the 2 is there is because we have 4 on both of them. So divided by 2. And then we perform a special type of algebraic manipulation. Well, it's not special, really. We can factor out a 4. And then from there, we can break up the radical of the 4. And the square root of 4 is just 2. So then all the 2's cancel out, right? It's like that's kind of the end result that we're going for here. So actually what I'm going to do here is I'm going to move this all over. I want to keep it all on one side. So that's equal to negative 2 lambda plus or minus the square root of 4 square root of lambda squared minus omega squared over 2. And then that's going to cancel out, that's going to cancel out, that's going to cancel out. And you get negative lambda plus or minus the square root of lambda squared minus omega squared. And there's your root. It just makes the answer look nicer in the context of what we're doing. Now, is it nicer? Who knows, right? But that's what we're doing. And if we can find, mass, spring constant, this damping constant, then we could just plug it into all these equations and get the answer, right? It's like that's all we got to do. So then our final solution for every single scenario. So the solution becomes x of t equal to C1e to the negative lambda plus the square root of lambda squared minus omega squared t plus C2e negative lambda minus the square root of lambda squared minus omega squared t. Like that solves every single scenario right there. That's the equation. Now, we can simplify this a little bit more, right? So, um, using, x to the m, x to the n equals x to the m plus n, we get x of t equals c1. Notice that you can basically break that up right there. And then you can also do it for this one. Oh, can't forget the t. Forgot the t right there because it's being distributed. And then e to the negative square root of lambda squared minus omega squared t. And then you can factor them all out. And this is the final solution. Now, from a physical concept, right? I want you to understand this. E to the lambda t, okay? Lambda will always be a positive number. And if you're wondering, how can I be so sure about that? Well, go back to what lambda is defined as. Mass and the constant of damping. I also said earlier, C is a positive number. Mass always has to be a positive number. So, by definition, note that lambda is always greater than 0, meaning e to the negative lambda t will always go to 0 as t goes to infinity. I want you to think about that from the perspective of energy. If there is any kind of damping, energy always has to be removed, meaning eventually, whatever this system is, it will stop moving. It has to. The energy is being dampened out by this exponential function, which is amazing. Like that's such a it's intuitive in our idea of physics, right? Like, oh yeah, if there's friction, it's eventually going to stop. But the math enforces that through the logic of e to the negative t is going to 0 as it goes to infinity through a limit, and then that lambda, because of how we define our constants, always has to be positive. That reinforces that notion, right? So it works out mathematically and intuitively through physics and energy that motion will stop eventually. So amazing, right? Now, what we'll have to do with these problems is we're going to have to do the three cases of real roots, real distinct roots, real repeated roots, and the complex roots. So everything we learned in 3.1 to 3.4 does come back into play. Now, one of the things that you have to be able to identify before you even solve a problem sometimes is whether or not this is the damp, over damped, or critically damped type problem, which again will come down to is it real, distinct, or repeated. So that's what we're going to talk about next. But do you actually have to memorize this equation? Like, that's a question that could be easily asked. The answer is no. You don't have to memorize this. You could always just solve it using the auxiliary equation. Like, I want you to go back. I could just solve this using r squared r and 1. Like that always comes into play. So you don't think that, oh man, I gotta memorize this equation. You don't. You can just solve it normally. But if you can memorize it, I mean, you could just skip the whole auxiliary process and go straight into the answer, right? So that's kind of the trade-off. If you memorize it, you can do less work. If you don't memorize it, you can just use 3.1, 3.3, and 3.4 techniques to get the answer every single time. This is just the final generalized solution. So, not an equation you need to memorize, but if you have it at your disposal, why not? Damping cases. So, this is going to analyze the behavior of lambda squared, because this is what's inside the radical, and this determines the sign and the complex roots of our solution. So, number one, if lambda squared minus omega squared is greater than 0, positive, we say it's overdamped. Okay, that just means there's a lot of friction. So the solution to this equation, okay, and every single solution will have e to the negative lambda t. There's no way to get rid of it. So e to the negative lambda t is a C1 e to the square root of lambda squared minus omega squared t plus C2 e to the square root of lambda squared minus omega squared t. Negative. I'm sorry, there's no negative here. No, wait, this should be a negative, I believe. Yeah, I'll double check right now. But yeah, it's overdamped. So what this means graphically, okay, if you drew this as a graph, wherever you start, you're just gonna go straight to zero. Like maybe there's enough initial force that you kind of go up a little bit, but you're just gonna basically decay down to zero. Like it's very quick. So whenever you have an overdamped system, it's a pretty quick, we're going straight to zero. So nothing special. It's kind of exactly how we expect it to behave, right? Critically damped, okay? It's the same thing as overdamped. It's still damped. So step two, or number two is if lambda squared minus omega squared is equal to zero, we say it's critically damped. And so our solution is almost the same thing. It's going to be C1 plus C2t. So what happens is the exponential part of lambda squared minus omega squared becomes 1, and the only lambda part is the e to the lambda t, right? So the graph of this is going to look very similar to our other one. Also, I should have always written this down. This is t, and this is x of t. So the vertical axis is the motion, the horizontal is time. So with critically damped, you have more opportunity to like go up, right? It's not as like in your face, we're going straight down, but it can. You can have a scenario where it goes down, right? It's just less exaggerated, like collapsing to zero. But at the end of the day, it's still damp, so it's still going to go towards zero, right? So these are somewhat the same. Critically damp, you might have more than one opportunity to go up and down, but again, it just depends on how much initial force you give it. And then number three, if lambda squared minus omega squared is less than zero, we say it's underdamped. And the equation of motion is going to be x of t equal to e to the negative lambda t. And no surprise here, if you recognize that this is complex, they're going to have sine and cosine. So C1 cosine lambda squared minus omega squared t plus C2 sine lambda squared minus omega squared t. There you go. Now this one looks a lot more interesting because um, it's going to look like this. So it has a sine curve, but it's being dampened and it's basically collapsing to zero. So what you could imagine is that the exponential curve is basically a boundary. That's what the e to the lambda t is doing. It's actually like collapsing it. It's like bounding it where it can't get away from it, right? That's essentially what's going on. So that's the underdamped case. It's still going to go to zero, but it just takes its time to get there. So this is all based off of frequencies and this lambda, but if you want to know, like, man, this is just too much notation. Is there another way I can kind of remember overdamped, critically damped, and underdamped? Absolutely. So we'll do it the other way. But this is a more, I guess, a frequency approach. Like if you're going into like system stuff, you'll probably see it more like this. But if you want a more, I guess, simpler approach, so, you know, cases of damping using M, C, and K. So given the differential equation mx double dot plus cx prime plus kx equals 0, we would say, let me make sure I get this correctly. C squared minus 4 times mk greater than 0. That's going to be overdamped. And then number 2, c squared minus 4mk equal to 0 is critically damped. And then number 3, c squared minus 4mk less than 0 is underdamped. So that's another way of identifying it just straight from the equation of what's given to you from the differential equation. There will be one homework question where you want to use this form. It's the last homework question. This will be pretty helpful in that respect. So uh, not a bad way. But like I said, you can interpret it however you want. So if you like the one that I did earlier with lambda and omega, by all means. But if you prefer to do it this way, it's the same thing. It's just, again, personal preference at the end of the day. So pick whatever you like. So now, through all that talking, let's finally do an example. And again, these are just word problems at the end of the day. It's the same thing we've been doing for a long time in this chapter, just adding a idea to it. So a mass weighing 8 pounds stretches a spring 2 feet. Assume a damping force. So this is how you're going to know what damping is. Assume a damping force uh, is equal to twice the velocity. Determine the equation of motion. X of t released from equilibrium going up 3 feet per second. So we'll add a new step just because maybe this might help you. Step 1, formula. So you can always use this formula now. So you can use any variation of this formula. Some people like to divide everything by m. I just write it in its most simple form. So mx double dot plus cx prime plus kx equals 0. Okay. Just that. I'm just telling myself I need an m value, I need a c value, and I need a k value. That's all it's telling me. Step 2, let's draw a picture, just so I know what this whole thing is saying. So mass, spring, okay? So it's telling me, hey, this mass, we didn't stretch it, right? This right here is equilibrium. So I didn't stretch it below or above. It's just at equilibrium. And then when it moves, it's going to go upwards at 3 feet per second. So this is your 0 point. This is the negative region. That's the positive region, right? Below equilibrium, positive. Above, negative. So if you're going upwards, that's a negative. And if you're going downwards, that's a positive. So we know the 3 feet per second is going to be negative going upwards, right? But that's just telling me, hey, this is equilibrium. I am starting at equilibrium because it's released from equilibrium, right? That's stated in the problem. Okay. Step 3, find M. Find mass. Actually, no, sorry. Check units. So we got pounds, we got feet. All right, we're good. So good. Step 4, find mass. Can you combine find mass, find C, find K all into one step? Absolutely. And I would recommend you do that. But just for this example, let's just do it all by one. So mass is equal to weight divided by gravity, right? Because weight is equal to mass times gravity. So then mass is equal to weight divided by gravity. So then M is equal to 8 pounds divided by 32 feet, which is a quarter. I'll use 0.25. If your fractions have nice decimal representations, go ahead and use them. I would use them. Okay. Step 5, find C. C is not complicated. C is just in the problem statement. So C is equal to twice velocity. So C is equal to 2, right? There we go. And then step 6 is to find K. Force equals K times X. So 8 pounds is equal to 2 feet stretched. So then K is equal to 4. There we go. Got a nice differential equation. So step 7 is to plug in. I know it sounds like a lot of steps, but I'm just thinking out loud, right? You can combine a lot of these steps into one step. So plug into formula. So 0.25x double dot plus 2x prime plus 4x equals 0. And then I'm going to multiply everything by 0.25, right? So that's a little trick for you. Or sorry, divide everything by 0.25. And according to my calculator, I would get x double prime plus 4x prime, if I recall. Nope, 8. It's an 8. Yep, I was thinking that too. And then I believe this is 64. Nope, 16. Going too far right there. There we go. Nice differential equation, right? Um, and we have our differential equation. So all I need now, okay, so far we know that damping, so again, a reminder, mass was weight divided by gravity, so 8 divided by 32, because 8 pounds, gravity is 32 by definition. They tell you that you're assuming a damping force is equal to twice the velocity. The velocity value doesn't matter, it's just they're telling you the constant of c is twice the velocity, so c is the factor in which it's related to the velocity. So twice means 2. 3 times would be 3. So the velocity value itself doesn't matter, right, for that value of c. And then finding k is just, it's usually in the first sentence. It weighs 8 pounds. It stretches at 2 feet. So you solve for k, right? So that's all we need to know for solving the differential equation. So now step 8 is solve differential equation. Again, if you know what the answer is ahead of time because you've memorized the solution form, you know what lambda and omega are, go ahead. But for us, we'll just solve it. So r squared plus 8r plus 16 equals 0. Now this is factorable. I believe it's going to be 4 for both of them. So r is equal to 4, negative. It's repeated root. So that means I have a critically damped system. Okay, so if the question says, is it damped, critically undamped, or underdamped, we would say critically damped. Okay, critically damped. So step number 9, plug into solution. Now, if you're wondering, um, do I need to like memorize like all of these different forms where I had earlier? You really don't. You can just plug them into your original solutions to the 3.1, 3.4. Those are just shortcuts. So I'll keep saying this. You don't have to memorize the shortcuts in 3.7. You can just go back to what you feel comfortable with, which is 3.1 and 3.4. Okay, so repeated roots meant that x of t is equal to c1e to the negative 4t plus c2t e to the negative 4t. Now, if I want to, I could factor out an e to the negative 4t, and I'm left with c1 plus t times c2, right? I can factor that out, and if you go back here now, it looks exactly like that, right? But again, you don't have to do that. Like that's not necessary, right? So I just want to make sure that you understand that you don't need to do that. So that's our answer. That's our equation of motion. Now we just got to solve for C1 and C2. Okay. So step 10 is solve for C1 and C2 using initial conditions. So our initial conditions. So they said start at equilibrium. What does that mean? It means x of 0 is equal to 0. Nothing has happened. Okay. The other thing they said is that it's going upwards 3 feet per second, which just means x prime of 0 is equal to negative 3, like that. And from there, we just calculate the values. So x of 0 is equal to 0. So 0 is equal to e to the 0 times c1 plus c2 times 0. So 0 is equal to c1. So c1 is 0. That can happen. You don't always have to get numbers for c2. And then taking the derivative, so finding x prime of t, you can kind of do this in your own way. You can do the first form or the second form. So this is a product rule. Actually, let me just write this down. E to the negative 4t times c1 plus t c2. Right the other way. So then the derivative would be f prime g plus fg prime. So negative 4 e to the negative 4t times c1 plus c2 times t plus f times g prime. So that would just be c2 because everything else becomes 0 and 1. And then now I just plug in 0. So using x prime of 0 equal to negative 3. Then we get negative 3 equals negative 4e to the 0, c1 plus c2 times 0, plus e to the 0 times c2. And again, I'll keep reminding you, e to the 0 is equal to 1. So negative 3 equals negative 4 times c1 plus 0 plus c2. So negative 3 equals negative 4c1 plus c2. C1 is equal to 0. So C2 is equal to negative 3. So x of t is equal to e to the negative 4t, and then C1 is 0. So negative 3. I'll put the 0. 0 minus 3t. So negative 3t e to the negative 4t is our final answer. Now we'll begin with the last topic of 3.7 for now, the alternative notation for uh, x of t equal to c1 cosine omega t plus c2 sine omega t. So this answer 100% correct. The problem fundamentally with this answer is that it's two functions, which doesn't make it intuitive to look at and know what information is. So because of a certain property with sine and cosine, that they're just 90-degree offsets of each other, someone discovered that using some properties of trigonometry, specifically like sum difference rules and stuff like that, you can actually combine them into a single trigonometric function, either sine or cosine. Now, from what I remember, I think the homework favors cosine in this class, but I've seen some people prefer sine. I think most people like the cosine variation first over sine, but again, it's just personal preference. So we're gonna basically convert two functions into one using some formulas essentially. So assuming C1 and C2 are not zero. Okay, so we're going to assume they're not zero. And this really works well for this specific type of problem. When it comes to damping, you can't do it because of the whole exponential. I mean, you kind of probably could with just ignoring the exponential, but usually you don't. So x double dot equals 0. We can express x of t as the following. So we're going to say x of t is equal to a cosine. I just want to see. So this is the way I do it, but it looks like on the, yeah, no, that's fine. We can do it this way. Omega t minus phi. The homework, we'll write it this way. C naught cosine omega naught t minus a naught. Like that's how the homework will write it. I think it's an alpha actually, not even an A. Okay, so like it's the same thing, same letters, just sorry, same process, just different letters. So we have formulas as follows. So where A, which will be equal to C naught, is going to be defined as the square root of C1 squared plus C2 squared. So this is essentially the amplitude. So A is the amplitude. That's the amplitude, how high and low it goes. Omega, which is omega naught, will be defined as the square root of k over m. Okay, we already knew that one. No headaches there for that one. So it's just k over m. Or essentially, it's just the value inside of the uh, cosine and sine. So you can see it right here. But in case you don't see it that way, you know it's k over m. Now, the one that's annoying is phi. Okay, we call this the frequency. If I remember correctly, it's a circular frequency. And then phi, which is equal to alpha naught, is going to be the arctangent, so the tangent inverse of C2 over C1. Okay? And so you gotta remember, this is the y value, and this is the x value, which is sine theta, and this is cosine theta. So depending on which quadrant you are dealing with, this will change whether or not you have to basically compensate or adjust. So a reminder from trigonometry, all of them are positive here. Sine is positive, tangent's positive, and cosine is positive, right? So if you think of your coordinates as x comma y, if you have a positive x value, but a negative y value, positive positive, negative positive, and a negative negative. So if you're in quadrant 4, so this is quadrant number 4, this is quadrant number 3, this is quadrant number 2, and quadrant number 1. Here you have to add 2 pi to get to this quadrant, okay? Um, for this one, you just don't add anything. And then if I remember correctly, this is going to be minus pi, and then this is going to be plus pi. So that's how you adjust for each of the quadrants. And that's kind of how you deal with it. I'll verify that that's true and post it later, but I'm absolutely sure on the quadrants 1 and 4, it's quadrants 2 and 3 that I always forget, but I'm pretty sure quadrant 3 is plus pi and then quadrant 2 is minus pi. But that's how you adjust your phase. And we call this the phase portrait. Not the phase portrait, sorry. Phase angle. There we go. So this is the phase angle, like that. So if a question asks you to convert, just convert it to that form, and then that's all it is. All right, just going to correct it. It was the other way around. So quadrant 2 is the plus pi, and then quadrant 3 is minus pi. And so there, we should be good with that. All right, after thinking about it more, I am pretty sure that it should be pi minus, and then this should be pi plus, or plus pi. I would verify this yourself, but I'm like almost pretty sure it should be that way because it didn't make sense when I changed it for you to add pi to get the quadrant 2, but I'm pretty sure like that is the correct way of doing it. But trig, right? Always fun and easy to do. But that wraps up 3.7. The only difference between this and 3.8 is the last function is no longer 0. It's now anything you want. So we get to do the whole process of finding a particular solution and then combining it at the very end. So if you feel comfortable all the way up to 3.7, 3.8 is just one more step of finding the particular solution. And that's pretty much it.